हेलो क्लास। हम पढ़ने जा रहे हैं हमारी हाइड्रोलॉजी। ठीक है, तो हमने लास्ट क्लास में पढ़ लिया था हमारी फ्लड रूटिंग तक, है ना। तो इस क्लास में हम हाइड्रोलॉजी पढ़ रहे हैं हमारी। ठीक है, हाइड्रोलॉजी हम कवर करें हमारी आईएएस मास्टर पब्लिकेशन की बुक से। तो इसमें हमारा कंटेंट देखते हैं हम। हमारा कंटेंट वाला पेज ये रहा। सो वी आर हेयर ऑन फ्लड रूटिंग। ठीक है, इट इज गिवन पेज नंबर 223 to 245। सो हम सो 223, राइट, 223 ये रहा पेज नंबर, चैप्टर नंबर 8। इसमें 223 पे हमने पढ़ लिया था हमारी फ्लड राउटिंग क्या होती है। ठीक है, हमने ये वाला फिगर 8.1 समझ लिया था कि हमारा ए पॉइंट से बी पॉइंट तक चैनल आ रहा है। तो फ्लड रूटिंग क्या होता है? इट इज़ अ मैथड by which we can find out the hydrograph at upstream side of any channel or stream if we have a flood hydrograph of upstream side, right? Known hydrograph of upstream side. So I covered this in last lecture. Now I want to cover this, the technique used in flood routing. ठीक है, and after then we start the basic equation in flood routing. Okay, so today our concern is basic techniques that is used in flood routing. Okay, so हम पढ़ रहे हैं अब हमारी चल रही है फ्लड रूटिंग। ओके, तो हमने फ्लड रूटिंग कवर कर लिया था। इट इज़ अ प्रोसीजर बाय विच वी कैन फाइंड आउट द find out the downstream hydrograph if we know the upstream hydrograph, okay, in any channel or a stream. So basic technique that is used in flood routing. हमारी क्या क्या टेक्निक है जो यूज होती हैं फ्लड रूटिंग में, राइट? सो द फर्स्ट इज hydrologic routing and the second is hydraulic routing. Okay, these are our basic two techniques of routing. The first one is also called lumped routing. Okay, hydrologic, in which there is a logic come. It's also known as lumped routing. Okay, and this hydraulic routing is also known as we can also write known as this. Okay, in this manner. So hydraulic routing is also known as distributed routing. Hydraulic routing is also known as distributed routing. ठीक है, in lumped routing we find out discharge. Okay, and in this discharge is a function of time. Discharge is a function of time at a given location. X. Okay, at a given location X, discharge is a function of time in our hydrologic routing, or we can say in our lumped routing, sorry. And in our distributed routing, discharge, this is our first point and this is our second point, this is our first point and this is a second point. Here in the hydraulic routing or distributed routing, discharge is a function of space and time both. Okay, here the discharge is a function of time and space both. Discharge is a function of space and time. Okay, both important. And in lumped routing, this is our third point. In lumped routing, we use continuity equation. We use continuity equation. Okay, and here in this hydraulic or distributed routing, we use continuity equation and momentum equation also. Okay, we use continuity equation and momentum equation. Okay, in this we use both equation, continuity equation as well as momentum equation. Okay, but in hydrologic routing we only use continuity equation. Okay, now we are going to basic equation used in flood routing. Basic equations used in flood routing. The first and the most important equation is continuity equation, because you can see here in both hydrologic routing and hydraulic routing, continuity equation is common. Okay, so the basic equation by which we can routing a flood hydrograph is continuity equation. Continuity equation. ठीक है, what do you mean by the continuity equation? It is the equation which represent the change in storage. Okay, inflow minus outflow equals to storage. The continuity equation is inflow minus outflow is equals to, क्या होता है हमारा, is equals to our storage. Okay, inflow, how we represent our inflow? Inflow is represented by I, minus for outflow we use Q, is equals to a change in storage. Okay, what is the change in storage? We can represent our change in storage ds upon dt, because storage is changed with time, right? For small, here we can write this equation for a small time interval. So for a small time interval, how we can write our equation number 1? I1 plus I2 divided by 2 into delta t minus Q1 plus Q2 divided by 2 into delta t is equals to change in storage S2 minus S1. Here what represent 1 and 2, and how we write this equation from this equation number 1? Let's discuss here. Suppose this is your Suppose this is your hydrograph of flood, okay, in which there is a no base flow, right? This is a curve. So here, if in y-axis we take inflow and at x-axis we take time. So if we talk about small time interval, that means a delta t. Here delta t is here. Here delta t is small. Okay. So for delta t is small time. For small time, if we mark these points of y-axis as time, this point is t1 and this point, let this point is t2. So this point is t1 and this point is t2. So this represent a small time delta t. Here this and this is corresponding inflow, right? This is at the time of inflow and this time of inflow. So I mark these points as I1 and I2. Okay. So we assume this curve from we assume here from point I1 to I2 the curve is straight. Okay, from point I1 to I2 the curve is straight. It's our assumption. Okay, this is our assumption. So how we can take what is the value of inflow between this and this? So we just take the average of this in time delta t. Okay, what is the value of inflow come in this period, this duration delta t from I1 to I2? So we just take a average of these values and multiply by delta t minus. Similarly we did it with outflow q1 plus q2 divided by 2. We just assume a straight line here, that's why we write q as q1 plus q2 divided by 2 into delta t. Okay, is equals to change in storage. Storage is change from due to this. At the time of t1 the inflow is I1, right, and at the time of t2 the inflow is I2. So that there is a change in the storage obviously. So here we take as a at point 2 S2 and at point 1 S1. So the change in storage is S2 minus S1. Okay, got it. So this becomes our continuity equation, which represent, this is come from equation number 1 when delta t is goes there. Okay, so I into delta t, here we write delta t as this delta t, small delta t. Okay, and I is taken as an average of I1 plus I2 and similarly with q, right? So now we come to the next one. This is our first in basic equation used in flood routing. The second is a differential continuity equation is also used for a steady flow. Okay, so the second is differential in differential form. Okay, in differential form the continuity equation for unsteady flow So here we assume that there is no lateral flow. Here is a small assumption is that there is no lateral inflow. Okay, with no lateral inflow. So the differential form of continuity equation is del q by del x plus t del y by del t equals to 0. This is our basic differential form of continuity equation where t represent top surface width. Okay, t represent top, here t represent top surface width, and here this y, x is space and t is our time. Okay, because we know that in hydraulic routing the function of discharge is depend upon both, the function is depend upon both time as well as space. Okay, so I think it's can't see properly, so I write here the y is depth of flow. Don't confuse t from the t that is we use in risk reliability. Okay, what it mean here from t is our return period. Okay, return period. Here is t, here t is not return period, t is return period in risk reliability वाले concept में. Okay, here t represent top width, surface width. So this is our basic techniques used in flood routing. Okay, and basic equation that is used in flood routing. In next class we continue further. Okay, so now thank you. In this lecture it's enough.